Recording. All right, so in class today we ended up talking, he ended up start off talking about the test, right? We need to go over that. He also had a brief review about the sort of like relationship between the fraction bound and the pressure of oxygen for myoglobin, right? It follows this like, he said, rectangular hyperboloid, I think. I can't remember the exact wording, but I'm sure he'll say it another time if it's important. And if you remember on the test, right, we calculated the percent bound of hemoglobin, or percent bound to myoglobin at lungs pressure of oxygen and at veins pressure of oxygen. We found that it wasn't very efficient at getting rid of oxygen because it just bound too tightly, right? So that's where hemoglobin comes in, right? So if we remember, myoglobin had a KD of about 3 torr. Hemoglobin has a KD of about 26 torr. All right, so insanely more useful when it comes to getting rid of stuff, because what happens is like it'll grab onto it and then it will not stay bound forever. Myoglobin is just too good at binding to oxygen. And we don't want that. We want it to be good, and we want it to be like sticky notes, right? If sticky notes were like used in industrial glue, right, you couldn't undo them and stick them somewhere else, right? So we need it to be just shitty enough so that it actually delivers the oxygen, but just good enough so that it will bind oxygen. That's where hemoglobin comes in. Now, if you remember, hemoglobin is essentially composed of 4 different subunits. And each one of these subunits binds to oxygen. And they don't actually have this rectangular hyperboloid curve. They have what is known as a sigmoidal curve, which looks something like this. See the little S shape there? That is a sigmoidal curve. All right, and this is characteristically, fraction of O2 bound and pressure of O2. This is characteristic of something called cooperativity. Basically, how good one of these subunits is at binding to oxygen is dependent on how many other ones are bound to oxygen. And so if we have our little setup, right, we have a hemoglobin, right, and it binds to n number of O2 molecules. That's in equilibrium with the bound form O2n, right? So if you remember that the fraction of O2 bound with myoglobin was, you take the pressure of oxygen, you divide that by the pressure of oxygen plus the KD. Well, for hemoglobin, because hemoglobin has this cooperativity stuff, hemoglobin, it's the same looking formula, KD, except we raise everything to this n power. All right, and this n is called the Hill coefficient. Don't ask me why it's called a coefficient, even though it's clearly an exponent here. Don't ask me, I don't know. But that's what it's called, right? And this will determine the YO2 for hemoglobin. All right. So this form right here, this Hill coefficient, is indicative of more than just like hemoglobin. Anything where you see cooperativity, you will see this Hill coefficient. Now, how do we find the Hill coefficient? He'll give it to us. He'll give it to us. But you need to know what a Hill coefficient means. So if we have a Hill coefficient of greater than 1, right, then that means that the cooperativity, right, when one site binds, the other sites are made more active. All right, so we call that positive cooperativity. All right, if we have an n less than 1, right, so we have like a fraction, then that means that whenever one site bonds to oxygen, the other sites become less able to bind to oxygen. And so that would be called negative cooperativity. Then at the very end, he kind of gave us a little example of how you figure out what the Hill coefficient is. I doubt that that's really going to be something we need to know. I feel like that's more of an FYI stuff. But basically, you could do some fancy math to linearize the sigmoidal curve, and then you can figure out what the n should be based on what you get. All right, so, and that was pretty much it for whatever he gave us, for whatever we went over in class today. I guess let's go ahead and do a couple practice problems. All right, so I have a feeling that because hemoglobin bonding wasn't on the test 2, it's going to be on test 3. And so it's probably good to start practicing that now. So let's say I have a partial pressure of oxygen of 30. I have a let's say I have a 30 torr. Let's say I have a KD of 20 or 26 torr. And I have a Hill coefficient of 2. Find me the fraction bound of O2. I'm gonna give you like 2 minutes. And that is 26 torr. All right, time is up. Okay, so how do we do this, right? So our fraction of O2 bound is going to be the pressure of O2 to the Hill coefficient over the pressure of O2 to the Hill coefficient plus the KD to Hill coefficient, all right? Our Hill coefficient is 2, our KD is 26, our pressure of O2 is 30 torr. So we've ended up with a YO2 is equal to 30 squared over 30 squared plus 26 squared. Working that out, we get our answer, plug and chug, basically. So yeah. Honestly, we don't really have that much for this test. That's part of the problem for this first class. We really don't have much of the problem, many problems to work through. Let me go ahead and see if we have anything from biochemical calculations. Here, I got a bit of a conceptual question for you. All right, so I've got two enzymes, right? One of these has so they both bond oxygen in the same way that myoglobin does. This is the fraction of O2 bound, right? They both bond oxygen just like myoglobin does. One of them has a curve like this, and one of them has a curve like this. All right, which one has a higher KD, A or B? Well, to figure this out, we remember that there is a relationship between the KD and the KD is the pressured O2 at which 50% is bound, right? So if we take a look, we say at this point, let's say this point is 0.5, right? Going through, right, we see that the solid line has a lower pressure at which it's 50% than the dotted line does. All right, so this is A, this is B, right? So A should have a higher KD. All right. So yeah, that pretty much wraps up this thing. Kind of a short meeting here. Not really much we can really go over. So yeah.